Hello, my name is Bowen Li. I'm happy to present our work, Heads Up, Unsupervised Constituency Parsing with Self-Attention Heads. This is joint work with Talk, Renaud, and Frank. Today, in the NLP community, we are seeing flourishing BERT and BERTology. Large-scale pretrained transformer-based language models have dramatically improved the state-of-the-art in NLP, including both natural language understanding and generation tasks. Monolingual pretrained transformers include BERT, Robota, XNet, Extra. Multilingual pretrained transformers include multilingual BERT, cross-lingual language model, XLM, cross-lingual language model Robota, XMR. There are increasing interests in investigating the linguistic knowledge pretrained transformers have learned implicitly during the pre-training phase. Such studies are always called BERTology. Special interests of BERTology study have been given to syntax. Researchers have developed several methods, but they all suffered some limitations. Goldberg 2019 introduced test suites that instantiate specific syntactic structures, but it requires a laborious compilation of language and construction-specific suites of sentences. Another common approach is to use general supervised probes, also known as diagnostic classifiers, but they sometimes fail to adequately reflect differences in representations. Recent solutions to this problem include control experiments or considering the effort of abstraction. And some researchers propose specifically designed structural probes, but it is designed for a specific syntax-oriented metric, not favorable to commonly used syntactic metric. It is therefore natural to use a parsing task to test whether pretrained transformers contain useful syntactic information. This enables us to test the syntax structure in general, rather than specific constructions, and doesn't require specialized probe. Here, we take advantage of the self-attention distributions to extract trees. The hidden representations can also serve as an alternative, but prior work shows that the attention distributions provide more syntactic clues under the unsupervised setting. The figure here shows the overall pipeline to extract trees directly from transformers. The left-hand side shows a pre-trained transformer. The purple heat map in the middle illustrates how likely a specific attention head is syntax-related. Each head corresponds to a self-attention distribution given a sample sentence, illustrated by 3 small heat maps. Intuitively, a syntax-related head always shows patterns like local chunking, while syntax-unrelated heads show other patterns like diagonals, columns, or other noisy patterns. First, we identify the syntax-related heads from the pre-trained transformers, and then we can just use the best head for parsing to get the parse tree. Of course, we can do a layer-wise ensemble. Instead of selecting the best single head, we can select the best layer and ensemble all attention heads from this layer, so we can conduct layer-wise ensemble parsing. Also, we can select the best K heads across different layers to perform a top K ensemble parsing. In this pipeline, Kim et al. 2020A proposed to use a top-down parser for head selection and parsing. Like we discussed before, there are basically 3 configurations for parsing: best single head, layer-wise ensemble, and top K ensemble. Specifically, given the self-attention distributions of a sentence, each token corresponds to a vector. Similarities between every 2 consecutive tokens can be computed. Then we can recursively split a sentence into halves by finding the minimum similarity in a top-down manner, and finally get a binary parse tree. The top-down parser suffers from its greedy search property. So the authors further propose to use a chart-based parser to consider all possible subtrees during parsing. But such existing unsupervised parsers all rely on an annotated development set for head selection, which is arguably not fully unsupervised. According to a recent MLP paper, an existing supervised parser trained on a few-shot setting can outperform all the unsupervised parsing methods by a significant margin. Here, we propose to rank transformer heads based on their inherent properties, such as how likely tokens are to be grouped in a hierarchical structure. Our approach here only relies on raw sentences. We get started from the chart-based parser we introduced before, which relies on annotated element set for head selection. In our case, our aim is to identify the syntax-related heads in a fully unsupervised manner. Here, 3 key maps show 3 syntax-related heads with high parsing performance. We can clearly identify local chunking and hierarchical patterns. Those key maps are our target. The equations in this slide come from the paper of the chart-based parser. First, the score of a parse tree defined as the sum of the scores of spans in the parse tree. Then the recursion is defined. The score of the span from position I to j is the sum of the compositionality score of the span from I to j itself, and the best possible split score. Since the distance is used as a measure, the smaller the score, the better the parse tree. Finally, the split score is defined as the sum of the scores of 2 subspans from I to k and k plus 1 to j. The figure on the right-hand side illustrates the span score computation. Basically, each attention head corresponds to a score of the parse tree. Intuitively, we can directly apply the score of the parse tree for head selection. But top-ranking attention heads show 2 patterns, attending to particular tokens and attending broadly. That's definitely not what we want. It means the algorithm focuses more on intrasimilarity and neglects intersimilarity. Naturally, we can introduce the cross score between the 2 subspans, but it goes to the other extreme. The algorithm turns out to focus more on the cross similarity. The top-ranking attention heads show clear diagonal patterns. That's still not what we want. Of course, we can additionally put a coefficient before the cross score, but it will introduce a tunable parameter. Here, we propose to introduce a length ratio to the recursion. Now we look at the term j minus I plus 1 over n. The numerator j minus I plus 1 is the length of the span from position I to j. The denominator n is the length of the sentence. This is motivated by the fact that longer spans should contribute more to the scoring of the parse tree. Since the intersimilarity or cross score always has strong effects on shorter spans. In this way, the inter and intrasimilarity can be balanced without introducing a tunable parameter. We name it the ranking-based parser. The only difference between our ranking-based parser and the chart-based parser is the head selection algorithm. Let's check out the experiments. We compare the top-down parser, chart-based parser, and our ranking-based parser with different ensemble configurations on the English Pantry Bank. For pretrained transformers, we use BERT, AxonNet, and Robota, with green and blue colors to distinguish 2 different settings, with and without a Dilbert set. We first look at the last 2 columns in each group to compare the chart-based parser and our ranking-based parser using top K ensemble without annotated element set. In this setting, our method outperforms chart-based parser by a large margin. If an annotated element set is available for previous methods, our method can match a top-down parser with top K ensemble and chart-based parser with the best single head or layer ensemble. The chart-based parser with top K ensemble produces the best parsing performance, which is not surprising since it uses the development set for head selection. It can be considered as the upper bound of our method. We also conduct experiments on 8 other languages from the SPMR dataset. We use a multilingual BERT, XRM, Robota as well pretrained transformers. Due to space limitation, we only report the average performance across different languages in this slide. More results and discussions can be found in our paper. For our ranking-based parser, we experiment with an additional cross-lingual setting, where we use attention heads selected on English to directly parse other languages. Surprisingly, this cross-lingual parser performs better than our parser using attention heads selected on the target language. We suspect that our ranking algorithm, for example, the inherent context-free grammar assumption, does not work equally well on all languages, at least for the annotation scheme provided by the tree bank. In this scenario, using English for head selection has a better chance to capture syntax-related attention heads. Compare with a chart-based parser with a best single head or layer-wise ensemble. Our cross-lingual parser can produce competitive results. Again, our method lags behind the chart-based parser with a top K ensemble. We are also interested in exploring to what extent the syntactic knowledge acquired by pre-trained transformers resembles human annotated constituency grammars. For this exploration, we infer a constituency grammar in the form of probabilistic production rules. Note that this study makes sense because we induce trees from the pre-trained transformers in a fully unsupervised manner, which means the trees are not biased to an annotated tree bank. As the figure shows, we're using a neural PCFG model to learn the constituency grammar from the trees induced from the pre-trained transformers. We learn the neural PCFG by maximizing the log joint likelihood. In this equation, X is the sentence, T head is a corresponding parse tree induced from the pre-trained transformer. The log joint likelihood is given by the sum of the log probabilities of production rules used in the derivation of the parse tree. Although tree structures are given during training, marginalization is still involved. All internal tags will be marginalized to compute the joint likelihood. For the grammar evaluation, we first evaluate the preterminal accuracy, which is unsupervised post-tagging accuracy. Inferred anonymized tags are mapped down to gold ones via many-to-one mapping, where each anonymized preterminal is matched onto the gold post tag, with which it shares the most tokens. The gold star means a PCFG learned from gold trees. We can find that our learned PCFGs, except for the robotic large, can outperform HMM baseline but are far from a state-of-the-art neural model. Our learned PCFGs produce similar accuracies as a PCFG learned on gold trees. We also evaluate the production rule accuracy on the English tree bank. Texts are mapped down to gold ones via many-to-one mapping. For the gold annotations, we drop our unary rules. For n-ray rules, where n is greater than 2, we convert them to binary rules by right branching and propagating the parent tag. The figures show that PCFGs learned from the pre-trained transformers lag behind the PCFG learned on gold trees by a large margin. This makes sense, as presumably the tree structures heavily affect non-terminal learning. To conclude, we set out to analyze the syntactic knowledge learned by pre-trained transformers. We propose a fully unsupervised parsing approach via self-attention mechanism that produces competitive results. We also present the analysis of the grammars learned by our approach. We hope our work can inspire follow-up study on the syntax learned by neural models without bias on existing tree banks. Here's a reference for this presentation. Thank you for listening.